So my name is Jim Hatcher. I'm a solution architect at DataStax, which means I get to go out and work with clients and help them set up DataStax products. So it's a fun job. I really enjoy it. I'm going to talk about GraphFrames today, and I'm going to talk some about open source GraphFrames, but I'm also going to talk some about DataStax specific GraphFrames because that's what I work with day in and day out. So, but I hope this will be an informative talk, whether you're using the DSE Graph or whether you're using GraphFrames in some other context. Quick agenda. I'm just going to talk about the building blocks, some of the concepts that go into GraphFrames, and kind of my mental model for how I approach this, and then I'll talk about some things that are in open source GraphFrames, and then do some DSE specific stuff, and then I'm going to tempt fate and try to do a live demo of some things. We'll see how that goes, and then give you some resources, and I'll post these slides to SlideShare, and you can, if it's something you're very interested in, you can track me down and find the slides, use them. So building blocks. So when I'm talking about GraphFrames, I can't move. When I'm talking about GraphFrames, so GraphFrames is a Apache Spark project. That's a way to do analytical work against a graph model. And so the roots of GraphFrames to me are pretty deep, and I think it's kind of interesting. So I tried to think of the best way to represent that, and I thought a picture would be good. So I came up with this kind of model, and DSE Graph is a component within the DataStax Enterprise stack, and the data layer, how the data is stored, is in Apache Cassandra. So that's a distributed database, and so that's kind of the foundational piece. And then the next piece to kind of understand is, okay, now what happens when we bring graph theory into the mix? Graph theory is a mathematical, some concepts Denise talked about signing up for a graph theory class in her keynote talk. And so really it says, how can we think about things as graphs, and what are vertices and what are edges? And then you kind of pull that into the concept of a graph database. Okay, now that I'm modeling my data in that way, how can I persist my data in that way? And then there's the Apache Tinkerpop library and the Gremlin traversal language, and you put all those things together, and those give you DSE Graph. So so far you have to understand a little bit about distributed databases, and you have to understand a little bit about graph theory and a little bit about graph databases, and then we have this stack down here at the bottom that involves Apache Spark. So if you don't know Apache Spark, it's a distributed execution framework. It's used a lot in the Hadoop ecosystem. It's used in the Cassandra ecosystem. It's used in others. But the idea is you want some way to distribute code execution across many servers. And so it's a pretty powerful framework. We use it in Graph for analytics, meaning we want to do some analysis against the data, whether that's some basic BI stuff, group counts, or whether it's some type of machine learning, that kind of thing. But you can also just think of it as a tool to do data ingest. You want to run some utilities against your data, that kind of thing. It's a handy thing for that. So, and then if you've kind of followed the progression of Spark, you'll know that the Spark world kind of started out with this thing called a RDD, a resilient distributed data set. And everything, we all learn about RDDs and what they do for us, and that they give us, resiliency in our data, and they're immutable, all these things. And then in the Spark world, things really moved from RDDs to data frames, which kind of enabled the advent of Spark SQL, and things like the Catalyst query optimization engine came into play, and Tungsten, which gives us some memory things. So in the Spark world, things have moved from RDDs to data frames for a lot of things. And then we bring in the idea of machine learning and graph algorithms. There's a lot of really neat machine learning algorithms you can do against the graph data model, things like PageRank and connectedness and centrality. And so there's a library in Spark called Spark GraphX, which gives us a way to do PageRank and these types of things against distributed graphs. And then as Spark started moving from RDDs towards DataFrames, the GraphX library jumped on that bandwagon and they said, okay, we're going to come up with a thing called GraphFrames. So to me, conceptually, the lineage of a GraphFrame, it's kind of complex and it involves a lot of things. So I think you can either look at that as sort of a daunting thing, like, oh man, if I wanted to get into GraphFrames, look at all this stuff I've got to learn. And that's true. But you can also look at it as, wow, that's a lot of powerful concepts coming together. And if I can get my head around that, my arms around that, there's some really powerful things I can do with it. So anyway, so and kind of the advent of all this stuff on the far end of the screen, we have a thing called a DSE GraphFrame, which is a specialized GraphFrame that takes the things available in the open source GraphFrame and adds a few capabilities onto it that make it interesting. So I'll say if this is a space you're interested in, and there's a book by Manning Publications called Spark GraphX in Action, and the author of that book, the first third of the book, he really says, here's a chapter on graph theory, and here's a chapter on graph algorithms, here's a chapter on functional programming, and he does a really nice job of just explaining what Spark is and explaining what graph is, and then kind of bringing them all together. And so it's really not a bad book for just learning Spark. So anyway, a good starting point if this is sort of GraphFrames 101 for you. So a lot of neat concepts kind of coming together. And after I created this picture, I realized that I had unwittingly created a graph. And this is my life now. I think it's actually a directed acyclic graph, which I also didn't do on purpose, but there you are. So. Okay, and then just one more picture just to kind of set the scope of what we're talking about. In the DSE graph world, or in the DSE world, we typically have, this is a common setup where we'll have two data centers, and one is meant to serve up OLTP traffic, and another one is meant to serve up batch analytics, OLAP kind of traffic. And Cassandra is kind of the underpinning that knows how to move data back and forth. Anytime you write to one, it automatically writes to the other. But we typically try to isolate, our real-time, low-latency traffic to one data center, and we'll isolate, our low concurrency, batch jobs to another data center. So most of the stuff I'm talking about would be things that would happen over here on the right side in the green world. So I just want to make that point. So, okay, so let's talk about GraphFrames a bit. Okay, so because of their lineage, they're just out of the box capabilities that they pick up, they're innately parallelizable. So if you have some process you're going to run, you don't have to worry about writing multi-threaded code. You don't have to worry about kind of managing that plumbing, because Spark does that for you. It's part of the plumbing built in, and it picks up the resilience and distributed execution ability of Spark. And then because it leverages data frames from Spark, you pick up Catalyst and Tungsten and the ability to do Spark SQL. So just kind of get that out of the way. Now the next kind of specific thing it does is a feature called Motif finding. And Motif is, if you're familiar with the Cypher query language that's popular like in Neo4j, so Motif is a subset of that language, and it kind of looks like ASCII art. I'll give you an example of it in a minute, but it's a way to say, hey, I'm looking for a pattern, a motif in my data. I'm going to describe it as this little picture of vertices and edges, and then I'm going to run it against the data. So that's one thing you can do in GraphFrames. Another thing that's built into GraphFrames are implementations of common graph algorithms. So there's some really powerful algorithms in here. I'm listing out some, but some of the ones that are really interesting to me are PageRank, which you may know as the main publicized way that Google does, or at least did in the early days, how they do search, how they rank their search results. That's named after Larry Page, the founder of Google. Shortest path is a very interesting algorithm you can do against your graph. Connected components. So these are all built in, and most of these come from GraphX. and they're done as RDD operations, and that makes a lot of sense. I used to think, in fact, in GraphFrames, the implementation of these things are really just wrappers around the RDD versions, and in some cases, I don't think it really even makes sense to try to make it like a tabular type of thing, because they're very the nature of their algorithms is that they want to parse through the graph and walk the graph. So anyway, so there's some great algorithms there. And then if there are some other algorithms that you wanted to write on your own, there are several methods that are made available to you in GraphX and GraphFrames, which are aggregate messages and Pregel. So if you wanted to do some other kind of algorithm that's not supported, you can do it on your own. And then I just wanted to kind of make the point that if you create a GraphFrame, what you do is in Spark you say, okay, I'm going to create this GraphFrame, and then I've got to tell you what my vertices are and tell you what my edges are. So you typically load that from I don't know, a text file or some type of binary format, GraphSun or something like that. And so you have to create the structure and you have to pull it in, and which is kind of a powerful idea in itself. You can say, hey, look, I'm going to store my data in a relational database, but then I want to go run some graph algorithm against it so I can export that data and then bring it into a Spark process and say, okay, this is, these tables in the relational database I'm going to represent as vertices, and these tables I'm going to represent as edges. And even though I don't store it as my system of record as a graph database, I can still take advantage of graph algorithms that I can run against it. So that's what I wanted to say about OSS GraphFrames. So DSE GraphFrames sit on top of that, and one nice feature of DSE GraphFrames, if you're using DSE Graph, to create a DSE GraphFrame, all you have to do is say spark.dsE graph and then point to the name of your graph, and it'll know, oh, well, you've already got a graph database. I know what the vertices are. I know what the edges are. I can immediately just start running an algorithm. So that's kind of a nice just kind of a shortcut. But you can also do the same kind of thing you do in OSS GraphFrames and say, hey, I want to load the data from this text file and union it with this data from this relational database. Anything you can bring into Spark, you can pull in as your vertices and edges. So one thing that DataStax brought into DSE GraphFrames that are not in open source is tinkerpop support. So there is the Motif finding built in, but you can also do tinkerpop support. So if you're in the DSE Graph world, any kind of OLTP interaction you're doing with your graph, you're doing through tinkerpop. So it's very nice to be able to say, hey, I've got this library of query patterns that I'm already running. I can just take those and I can pull those into GraphFrames and run them in a scan operation. However, there's a catch there that most of the tinkerpop API, the Gremlin API, is supported, but there are some things that are not. So you have to be a little careful there. So some notable exclusions, things that are not supported are the repeat step, the union step, the as and select step are three that are come to mind. So and really I was going to give my opinion as to why I thought they weren't supported, but over time I think we'll continue to see more and more of those steps supported in GraphFrames. GraphFrames are very good for operations that you think about as a big scan across your graph. Typically in OLTP mode, you're not going to be scanning through your graph, say, give me every customer vertex label and do something with it. You're going to be very discrete and make very small operations on the graph. But if you want to do something like get me a count of vertices, you'd think that'd be a very simple thing to do. But in OLTP mode, we don't let you do that. So just doing something like that, it's really handy to have GraphFrames in the mix. So here's some common things you can do in your graph. Jonathan Lacefield was just giving a talk about how can you understand the cardinality and summary statistics of your data to avoid super nodes. So this could be an option that you'd want to do. Just do some simple group counting of your graph. And if you have this workload isolation setup where you have OLTP traffic over here and batch traffic over here, you can do that without affecting your, your production, whatever kind of traffic. So it's good for that. Another thing that GraphFrames is really good at is anything you want to do against your graph that's going to cause you mutations. So we tend to think about GraphFrames as like an analytical thing. You're trying to get insight into your data, but it can also be used for just very like utility kind of things. So doing an initial load of data into your graph, GraphFrames is a very good tool for that kind of thing, because it's parallelized already. If you have data like in text files that you're going to pull out and load into your graph, you can put those on a distributed file system like DSEFS or HDFS. Use Graph to read that data, and it can, if you've got a 30 node Spark cluster, you can have 30 nodes just cranking data into your graph. So it's one of the fastest ways to push data into the graph in batch. And then another place I see customers using it is like in a dev environment. Maybe you've got a model that you're starting to code against, and schema, and you decide, oh, we've got a super node problem, or we've got some kind of problem in our schema that's not working well. We want to alter our schema, split this vertex label into 2 or something. But meanwhile, you've loaded 100 million vertices into your dev environment. You don't want to just wipe it out and redo it. So you can write a GraphFrames job that says take the data, push it, transform it, push it into the new schema. So it's handy for that. And then things like, hey, I want to go drop all instances of vertex label X. We messed that up. We're going to reload it, so I just want to zap it. It's handy for that kind of stuff. Let's see. And so there's two methods. I'll demo one in a minute. One's called update vertices, and one's called update edges. So those are two things that I'm 99% certain are not in OSS GraphFrames that are in DSE GraphFrames that are really handy. Okay, demo. I'm going to give this a shot here. Okay, so I'm going to bring up a tool, DataStax Studio. Try to make that bigger, I guess. You guys see that okay? So for this demo, yeah, there it is. For this demo, I'm using the killer video reference application. This is something that DataStax uses as in our training videos and that kind of thing. It's kind of our reference architecture. So you can see the schema over here on the right. What we have is a database that has movies, and then we have actors that acted in a movie, and directors and that kind of thing. And we have users that rated movies, and so you can see the schema here. I'm looking at this in DataStax Studio, which is just a notebook solution we have. It's really meant to be like a developer tool, just to help us interact with Graph. So, okay, so just kind of as a starting point, this is a typical Gremlin query we might run in OLTP mode. We're saying, go to the graph, give me all the vertices that are of type movie, and then find me the specific one that has a title of I Am Legend. And we get that back here. And I just want to point out that by default, if I take off this has clause and try to run that query, Studio will tell me, hey, you can't do that because that requires a scan of that vertex label, and we don't allow you to do that. In fact, the message actually says, graph scan is not suitable for anything other than toy graphs, which is I always thought was kind of a passive-aggressive message. But so you can tell it, I specifically want to allow scans, but the whole idea is that that's not a scalable thing. That's not something you want to be doing against a graph that has a billion vertices. That's going to take minutes to do that. So, but I can in kind of normal mode here. Whoops. just if I give it a specific entry point into the graph, I can do that. So, so this is kind of the typical way that we interact with graph. If this is something we're doing that's an OLTP operation, this is the kind of thing we're doing. So in Studio, I can say, okay, I'm going to click on that movie. I'm going to expand its neighborhood and include anybody on the actor edge. So if I do that, Studio will kind of bounce around and show me all the actors who are in I Am Legend. And then if you wanted to, you can keep kind of expanding out and doing that. So just want to give you a sense of that. Now, if I wanted to do a query like this, what I'm saying is give me movies that are I Am Legend, and go out, find me all the actors, and then group, give me a count of actors that are in that movie. So that's telling me in I Am Legend we have 8 actors. So if I wanted to, I could comment out this specific clause, and again I get this message telling me that this scan is not suitable for anything other than toy graphs. So I can cheat and say that I want to allow scans to happen, and so I'll do that. And then if I run this query, it will actually show me the results. So we can see that Harry Potter and the Deathly Hallows Part 2 has 44 actors in it, and other Harry Potter movies have a lot of actors in them. So this is an example of, I'm going to go, this is something that basically scans through the graph, does some aggregation, and give me the results back. So it's not something I typically do in OLTP mode. So this is my first example of something that would be good to do in a GraphFrame. So let me switch over to a Spark shell. So this is a Spark shell. It's just an interactive command line that I can use to interact. So let's see. So just to kind of get a sense of this, if I took, well, first let me create an instance of a GraphFrame. So I'll say val g. Is that big enough? Val g equals spark dot DSE Graph killer video, which is the name of my graph. And when I do that, Spark should tell me I have a DSE GraphFrame. So it says I have a variable here called G, which is of type DSE GraphFrame. So now if I run this, I'm saying give me a count of all the vertices in my graph, which it'll do, and the result of that is a data frame, so or a traversal. So I need to do a show to tell Spark to actually go execute that and give it to me. So it says I've got 10,797 vertices. So I can break that down further, and I could say give me a count of vertices by their label. So I can run that. Forgot my show. And so then it breaks it down by labels for me. So it's a handy little tool. Like if you're just loading data in your graph for dev, and you think, well, I just loaded a text file with 10,000 records. Do they all make it into the graph? Handy little thing like that. But this example that I did in the other side, if I try to do it, it actually runs into some problems. And in this case, it's because I'm not referencing the right library. But I can tell you, I don't think the group count by is supported in GraphFrame. So here's an example where we have kind of limited Tinkerpop support. However, in GraphFrames, we kind of have several ways of thinking of how to do things. So because we're operating in GraphFrames, which sits on top of data frames, we have access to do things in Spark SQL. So if I come over here, I'll run these two statements. And what I'm saying is go out to my graph called killer video, and all the vertex instances I want to register as vertices, and edge instances I want to register as edges. And now these are available in my metadata store. So if I want to do a SQL statement against those things, I can do that. So if I paste that in over here, and then do movies and actor counts.show, that'll kick off a Spark job and run that. So this is a very comfortable space for me. I've spent a lot of time in the SQL world, so you know, thinking about this as a tabular type of thing that I want to scan through and do a group by statement or a having statement is a very comfortable space for me. And I would think a lot of people out there have, you know, come to the graph database from the relational database world, and so this is a good thing to do. And you see we got the same Harry Potter movies as our top answers here. So and I'll tell you in general, you know, this is an example of something we saw we could do in Studio in OLTP mode, or we could do in GraphFrames in batch mode. Generally speaking, this stuff runs much faster in GraphFrames than it does on the OLTP side, and I think probably the bigger takeaway is, even though I can in this instance get this to run, I only have 10,000 vertices in this graph. If I had a 500 million vertices graph, this is not going to scale well. This would probably time out, or might run for, I don't know, hours or something. But on the Spark side, you know, it's built to do that. So pretty powerful thing. Okay, next example. How am I doing on time? I might skip this one for now and come back. But this is another Spark SQL example where I'm looking for actors who've appeared in movies that are across multiple genres. Okay, so let me come back to that one maybe. So I'm going to give an example of motif finding, and if you see here, what we have is we say g.find, so where g is our graph frame, and then we pass it the string, which I like to describe as ASCII art. This is the motif language. So what I'm saying here is I have a vertex that I'm going to call movie, and it's adjacent to the vertex called person, and that's connected by an incident edge called E1. Now what I call those doesn't matter. I could call it X, Y, and Z. Doesn't matter. The only context it matters in is if you put another statement over here and you call it the same thing, Motif's going to link those together and say, oh, that's the same instance of that vertex. So here I'm saying, okay, I'm looking for movies that are connected to persons, and then I'm looking for movies that are connected to genres. And so that's kind of the first step. You say, here's the pattern I'm looking for, here's the motif I'm looking for, and then you can apply this filter statement, and this looks very much like a SQL where clause. And I could say, that thing that I referenced as person above, I'm looking for specifically the label where that's the person. So that's how I say, that's the person vertex label in my graph, etc. So these lines here, I'm just kind of giving it some plumbing. And then here I'm saying, and where that genre is in comedy. So I'll just run this. So that gives me a data frame back. And if I show that, we'll see that a Spark job kicks off. And should give me a list of movies that were in, people who acted in movies that were in the comedy genre. So I'll say one thing I found about using this motif finding, a lot of the stuff you could do in motif, you could also think of how to do in a Spark SQL kind of way. So it's given me the first 20 rows. So here's Sally Phillips acted in Bridget Jones' Diary, and that's comedy. So one of the things I found is that if you take that data frame that it built and you do an explain on it, Spark will tell you basically the plan that it's put together to build this. And sometimes I do get into actually reading the details of this. You know, there's things in Spark you want to avoid, like shuffles where you have to move data across nodes and things like that. And you can get into this, but sometimes if I'm looking to do something, I think, oh, I could do that as a motif, or I could do that as Spark SQL. Sometimes I'll write it both ways, and then I'll look at the explain plan, and you can get into looking at the details, but generally speaking, if the explain plan is this long, 20 lines long, and this one's 100 lines long, the 20 lines is going to be a lot faster. So I found in general, if it's something I could do in both, that the Spark SQL really ends up being faster in most of my experience. So, like that. This is the explain plan for this Motif guy. If I look at the explain plan we did for the movie and actor counts, let's just get a sense of how long that was. Much shorter. I mean, we're doing the same thing, but just kind of get a sense of it. If you've seen a short plan, that's usually good. Okay. All right, so the next thing I want to demo is doing shortest path. But let's take a look at something real quick. So what I want to show here is I'm just doing a traversal where I say, find me a guy named John Wayne, and then go into this repeat step, limit it to 10 seconds so I don't create some thing that goes on forever. And what I want to do is, if we look at our schema, start at the person. I want to go in on the actor edge, which gets me to a movie. Then I want to come back out on the actor edge, which gets me back to a person. That's what we're doing here. And then we're saying, give me the simple path. So don't create any cycles. Don't go from John Wayne to Green Berets, back to John Wayne, back to Green Berets. Only go simple paths, non-acyclic paths. Whatever. You know what I'm saying. And so if I run this, it's just going to start at John Wayne and just going to kind of traverse for a while. And what you see here is that John Wayne was in The Sons of Katie Elder, and also in that was a guy named John Littell. So the shortest path algorithm in GraphX, I learned as part of putting this presentation together, only follows edges in their direction. So if you say, I want to find the shortest path from John Wayne to Jimmy Stewart, it'll start at John Wayne and it'll go out, 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 out. It'll never go in. And so in this graph, if I start at John Wayne and try to go out, there is no out. So so the shortest path example I want to do is for, what's the shortest path from John Wayne to Jimmy Stewart, and so this won't work. So in order to do a shortest path algorithm on this, what I'm going to do is create shortcut edges from every actor to every other actor who's worked in the same movie. So because I can do mutations in GraphFrames, I'm going to do that here. So I won't get too much into this, but what I do is I start at a person, and I go to an actor, and go to a movie, and then go to another actor, and I join that all together, and then I build a data frame here that's an edge that says I'm going to create an edge between actor 1 and actor 2, and I'm going to call that thing work together. So the first thing I want to do, go back to DataStax Studio. What I want to do is alter my schema to create a new edge label called worked together between people. So after I run this, we'll see that the schema change over here on the right. So you'll notice this recursive edge that Jonathan warned us that might cause some supernode issues in the last talk, but there it is. And then I'm going to run this fella in pieces. So we create some data sets that are basically pointing to structures in our graph. And then we say, I'm going to do this first step, which joins, actors to people. I'm going to do this next step, which joins that result to movies. The next step, which joins that to actors again. And then I create this data frame called shortcut edges. And the shortcut edges, when I'm done, I have a data set that has a column called source, and I have a column that has a name DST, and then I have a thing called tilde label. So those are the 3 columns that are required in GraphFrames for edge structures. They basically say, I'm connecting this source to this destination with this label. So then what I do is I call a method on my GraphFrame called update edges, and I'm going to pass in that shortcut edge. And this has worked for me a couple times, and it went weird on me one time, so hopefully the demo gods are smiling down upon me. This is going to work. No. So hang on here. I had this problem earlier. I think it has something to do with the way I'm pasting it in. Hey, while I'm pasting this in, Denise, could you like dance or I don't know, soft shoe? Yeah.
Hey Jim, I got a funny graph joke.
Let's hear it. Let's hear it.
Two edges and a vertex walk in the bar. Bartender says, no, we're closed. You can't come in here. We don't want any incidents with you.
Ah, that's bad. I know. Do you?
Just proof that there's no funny graph jokes.
It's like the DBA walks into a bar and he goes up to 2 tables and he says, "Do you mind if I join you?" Okay.
Walks into the bar, walks up, I'll have a beer. I'll have 10 beers. I'll have 1 million beers. I'll have A, B, C, D, E, F beers.
Nice.
Anybody else?
All right, so it broke on me. All right, but what was supposed to happen was we'd see a work together edge between John Wayne and John Littell, and then an edge going the other direction between John Littell and John Wayne. And by the magic of television, I have actually run this and stored the results. So here's an example of how you run shortest path. One thing about running these graph algorithms is that it uses Spark checkpointing, so you have to set up a checkpoint directory on a distributed file system of some kind. So I'll just run that as a little plumbing, and then what you do is we're going to say I want to run from my GraphFrame. I want to run shortest paths, and you pass it a set of landmarks, and a landmark is what you're saying is I want to go through my whole graph and say, what's the shortest path from every vertex in my graph to whatever these landmarks are. And you can just give it one thing, or you could give it 1,000 things, whatever. So in this case, I'm just going to pick John Wayne and Jimmy Stewart. So I need to pass in a sequence of the IDs of John Wayne and Jimmy Stewart. And in GraphFrames, the IDs look a little weird, so I'm just going to run this statement. So you can see John Wayne's ID is the person, which is the vertex label, and then like a base 64 encoding of the keys. So anyway, I have John Wayne's ID and Jimmy Stewart's ID, and then what you would do is pass those in here, pass in the landmarks, and then you'd run it. So I did this earlier, and I stored the results in Cassandra. And this is something we see clients doing a lot, where you want to go run some algorithm. Maybe it's a personalization algorithm or edge weighting algorithm or something. You want to do that. You want to store the results, and then you want to like serve them up in your OLTP system, that kind of thing. So here's a little shortcut method that we have in DSE that says, given a data frame, go create me a Cassandra table with a schema that matches that. So that's a little shortcut thing. So this created a table called shortest paths in a key space called test, and then I kind of tell it what my keys are. And then what I did was I took the results of that and I wrote it out to that table. So I'll just bring up this other terminal window. And so I have a table here called shortest paths, where I stored this output. And so here's one of the results of our shortest path algorithm. This says for the vertex label person with that key, this is a person called Sarah Valiente. She is 6. From her to John Wayne is 6 places away, and from her to Jimmy Stewart is 5 places away. So, so I'll store that in Cassandra. And you can see if you actually go look at Jimmy Stewart's record, it says Jimmy Stewart is 0 hops away from himself, and he is 1 hop away from John Wayne. So apparently Jimmy Stewart and John Wayne acted in a movie together. Anyway, that's an example of some shortest path. And so this algorithm on about 10,000 nodes took maybe 5 minutes to run. It scans through the whole graph and creates all the shortest paths. So it's pretty powerful stuff, and it's just canned. Like you don't have to tell it how to traverse the graph. You just tell it, go out there and just scan through this thing. It's pretty cool. So that's my example. I got some resources here. I'll just talk through them real quick. This first thing, I guess I can present again. This first thing is the GraphFrames page, and it's got a little description and documentation about how you can use the different algorithms, sample on how to do, connect the components, etc. This next link is the GraphX code, and it's a surprisingly small code base. You can go out there and see how they do shortest path and all. I'll tell you, most of it's based on message passing algorithms. And my colleague, Mr. Paras-Mera, is going to do a talk this afternoon where he kind of gets down into the details of how some of that works. So if that's interesting to you, make sure to attend that. This third link is the GraphFrames code. This fourth link is a presentation that Russell Spitzer and Artem Aliev did. These are two of the engineers at DSE who wrote DSE GraphFrames. So it's pretty neat talk. And some blog explains some things about it. And then this last link is the Manning book I was talking about earlier, GraphX in Action. It's a book about GraphX, but it has several chapters on GraphFrames. And if you want to get started in it, I'd highly recommend it as a really good place to kind of jump in. Okay, well, thank you for a chance to talk.